Hey folks, I've missed you. So my first plan to talk about today is to talk about the limit definition of the derivative. So I know that there's some people in our class who have maybe taken calculus and talked about derivatives before, and there might be some other people in our class that have never seen this before. So I think this is a good topic to kind of talk about this week at a distance, because for some students it might take a lot of practice to get used to these. And for other students, it might just be a bit of review. So, and a little bit of, something in the middle for some of the rest of you. So we're going to start with the limit definition. That's what this video is going to be about. And then we'll jump and talk about some of the derivative rules. But I think it's really important that we go through the limit definition of the derivative first, because this is how 21A is going to start to introduce derivatives. And it is important that you can work out the derivative using the limit definition. Because they will ask you to do it on tests. I will ask you to do it on our final exam, and your teacher in 21A will definitely want you to do it this way. So if you know derivatives already, you can kind of just use your rules to check. So here we go. Let's talk about what it is. All right. Still kind of getting used to this. Here we go. Okay, so I wanted to start with sort of two definitions here. So I drew a secant line and a tangent line, and I just want to make sure we're very clear about what the difference between the two is. So this secant line is drawn on this function, and it goes very clearly through 2 points, right? Goes through 2 points. So I sort of labeled those 2 points on there, okay? Now, if I wanted to get the slope, right? So if I wanted to, maybe I'll write this as M of the secant line, right? So M represents the slope, right? If I wanted to do the slope of this, the slope of the secant line, I have the 2 points, right? So to get the slope is easy. We'll just do the difference between the two y values, y2 minus y1, over the difference between the two x values, x2 minus x1. Okay, so I'm sorry, I'm going to try to keep this from jumping around like that. I'm still getting used to it, but here we go. Okay, so we've kind of gone through what a secant line is. Now, a tangent line is a very special kind of line because it is only going to go through the function once. It's only going to go through 1 point on our graph. And it just sort of, grazes the function, right? And so to work out the slope of a tangent line is a little tricky, okay? So I'm just going to write tricky, and then I'm going to kind of motivate this with an example. So let's move on and talk about that. So how on earth are we going to get the slope of a tangent line? So I wanted to work through this one. So I've kind of got a similar shape there. I've got f of x is equal to x squared, right? Okay, and so I've graphed it on there. And let's say we're interested in the slope of the tangent line, particularly at x is equal to 1. So I've plotted that point on there, 1, right? And its y value is f of 1, in this case 1 squared, which is 1, okay? Now, if I wanted to get the slope of this tangent line, what we're going to do is we're going to sort of build out a line here that's just a little bit of ways. So I'm going to go between this point, and I'm going to construct a line that goes between those 2 points. Now, bear with me here. I'm going to have to zoom in and try to make this work. Okay, so here we go. So we've got our line that goes through, pretend with me for a second that that's a straight line, and it's going through those 2 points, okay? And I've picked some point here that is just, a little bit a ways from 1. So, this x value here is 1 plus a little bit. So let's call that little bit h. So the distance between those two, that distance is h. Okay? And so this point up here, right, this y value that this is sitting at is f of 1 plus h, okay? And we know how to get the slope of that red secant line. Remember, we talked about secant lines have 2 points, right? And we've got the 2 x coordinates and the 2 y coordinates. If I wanted to get the slope of the secant line here, I would do f of 1 plus h minus f of 8 f of 1, right? That would be the difference between the two y values. And then the difference between the two x values would be 1 plus h minus 1. Okay? So that expression there is giving me the slope of the secant line between those 2 points. Now, what I want to really talk about is if that h value gets smaller, right? If those 2 points get closer and closer together, that red line, the slope of it is going to get closer and closer to the blue line. So I put together a simulation here to kind of demonstrate that for you. So just so you can kind of see, this is the same graph, y is equal to x squared. I've got my blue tangent line grazing at 1 point. That's the slope I'm trying to get. And then here I've got this secant line, right? And you can sort of see I can drag it around. And then can you see the numbers here on the other side? I think you can, right? So you can see here that this h value in the bottom left-hand corner, when I drag this around, if I drag it that way, h is getting bigger. But if I make h get smaller, if this point gets closer and closer to the other point, let's say it was like super close, that's pretty close, right? You can see that the slope of the red line and the blue line are really close to each other, right? And if h gets even smaller, wow, those are almost the same line, you know? And if h gets even smaller, they get even closer. So the idea is if h is really, really, really small and gets really, really close to 0, then the two slopes would be exactly the same. Now, let's go back to our sort of expression here that we had here, right? So if you look at the bottom there, I've got 1 minus 1, right? So the bottom here is just h, right? So I can't make this h value 0. That would be if, you know, the 2 points were right on top of each other. I can't make h 0 because then I'd have a divide by 0 problem. But if I want to sort of consider what happens as h gets really, 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 really small, we talked about how to do that, right? We talked about that back when we talked about limits, right? We can take the limit here as h goes towards 0 of this expression, right? So we're taking, you know, the slope of the secant line between 1 and 1 plus h, and if we consider what happens as h gets really, really small, that's going to give us the slope of the tangent line. So maybe I should write that in here. Slope of the tangent line is going to be equal to this expression. It took us a little bit to get there. Let me move this. There we go. But there it is. So we're going to go through. We've talked about how to evaluate limits now. So you should be able to go through and evaluate this expression. So let's start here. So we're going to have to keep writing this limit sign on this left-hand side, just like we had to do before. Now the bottom we've simplified, so there's only an h down there. Now on the top, we have f of 1 plus h and f of 1. Now we know here in this case what the function was, right? We were doing this for f of x is equal to x squared, right? And so we're going to just plug that in here. So if we have f of 1 plus h, that's going to be 1 plus h squared and minus 1 squared. And then there might be some algebra we can do there to try to get this to simplify a little bit. So we'll have the limit as h goes towards 0. We have to write that every time. Now what we could do is we could FOIL out that top. The bottom is just going to stay over h. Nothing has changed. But on the top, we could take that 1 plus h and FOIL it out. So 1 plus h times 1 plus h. If you FOIL that all out, it'll give you 1 plus 2 h's plus h squared, and then minus 1, right? That comes from the minus 1 squared. So we FOILed it all out. Then from there, we're going to see what else we can do to get this thing to simplify. And I noticed that there's a plus 1 and then a minus 1 on the top, so those sort of cancel each other out. Then from here on the top, both of those terms on the top have an h in them, right? So we can factor out an h from the top. So if I factor out an h from the top, I'd be left with, from the 2h, I'd be left with a 2, and from the h squared, I'm left with an h. And if I factor out that h from the top, now we've got the top and the bottom to cancel, right? And so because I've got the top and the bottom to cancel, I'm just left with 2 plus h. And I'll write this out one more time with the limit sign. Seems a little excessive here, but we got it. So from here, now you're to the point where you can just plug in h is equal to 0, right? Because if we plug in h is equal to 0 here, this thing goes to 0, and we're just left with 2. Woo! All right, so let's go back and look at that picture and talk about what that means. So what that means here is, oops, that slope of that tangent line, that blue line, let's see if I can highlight it, right there, right? That blue line, it has a slope of 2. Now, things they could change on you here, right? They could give you a different value that they want it to be the slope of the tangent at. So, you know, maybe they want the slope of the tangent line at x is equal to 2, right? So then you would just change all of these numbers here to 2's and work through the algebra, right? The other thing they could do to you is they could change the function, right? In this case, it was x squared, but we could do it for sort of any function, x cubed, sine, cosine, exponential functions, and we're going to work all through those in videos this week. But that's sort of the basic idea of getting the slope of a tangent line. Now, the slope of a tangent line, that is what we're going to call the derivative. So the slope of a tangent line is the derivative, okay? And so they're using, I'm going to use this notation, f prime of x. So it's like a little apostrophe next to the f, okay? And that's going to represent the derivative. And then this is the definition that we just talked about, right? So you're doing f of x plus h minus f of x over h. That comes from pretending like it's a secant line with 2 points, and then considering what happens as those 2 points get closer and closer together, right? As h goes towards 0. So let's say if I wanted to work out the derivative, and I'm just keeping this function exactly the same for now. F of x is equal to x squared. Let's pull up this derivative so you have it. It's moving around on me. Okay, here we go. So the derivative here is the limit as h goes towards 0 of, and then we're going to plug in. So our function is x plus h squared minus x squared over h. So I'm just plugging in what the function is. Then from there, oops, I'm going to FOIL out the top just like I did before. So x squared plus 2xh plus h squared. Maybe that might take you a little bit longer than me. That's okay. Then from there, the two x squareds cancel, right? And now you'll notice that all the terms on the top have an h in them. So we can factor out that h from all the terms on the top. So I'm left with 2x plus an h over h. And then from there, now our two h's cancel. We no longer have a divide by 0 problem. It's not 0 over 0 when we try to take that limit. And so we're just left with 2x plus h, and when I take the limit of that as h goes towards 0, it gives me 2x. Okay? Because the h, this part here, is going to go to 0, right? So if you have taken calculus before and you have talked about derivative rules, you might notice that 2x sort of matches up with what you get using the power rule. If you don't know what that is, there'll be a video just shortly about that, and we're going to talk about that. But I think it is important that you can get the derivative using the limit definition. And if I want you to use this long way of doing it, I will say explicitly, you know, using the limit definition, so that you know that you kind of have to use this formula in order to calculate out the derivative.